So the idea is that you want to use a restricted Boltzmann machine. So in restricted Boltzmann machine, you have some input, you have some hidden states, and you have some weights, but your hidden states are just binary. We are doing semantic hashing. And so the marginal distribution over visible count vectors is P of V is equal to summation over H e to the minus energy of V and H divided by summation of U and G e to the minus E of U and G. So that's why in the previous lectures I talked about Boltzmann, restricted Boltzmann machine. And the term restricted, it means that these are bipartite graph. So these things are not related, connected. These are related to the other parts, not together. That's why we call it restricted. And I just recall that energy of V and H is just minus lambda I Vi plus log of Vi minus the term for bias Bj at j minus Vi at j Wij. And to perform a gradient ascent, because it's different, we want to maximize it, in the log likelihood is Wij is just epsilon of log of P of V divided by Ij. So epsilon is the learning rate times the Vi inner product of Vi and Hij. When I say data, it means expectation with respect to data distribution minus Vi at j model. When I say it like this, it means that it's expectation with respect to distribution defined by the model. And Wij is, therefore, we can write it as Vi at j data minus Vi at j reconstruction. You have a text in the input, you give it a text, and it gives you the reconstructed distribution over words. So with word count. It gives you a text, but your text is represented by these word counts. So that's why we represent texts. So this is the text that, so this is the distribution over text, and this is the distribution over words. So to make codes binary, we just add the Gaussian noise at each layer. And the next article that I'm impressed is done by University of Copenhagen, 2019. The title is Unsupervised Neural Generative Semantic Hashing. We use it for fast similarity search in information retrieval. And it is an unsupervised general semantic hashing, and it is based on ranking-based semantic hashing. It uses ranking, because then we can, so I should say that it consists of a variational component, reconstructing original document, and also, so you are familiar with these in the context of all variational autoencoder. But the thing that is new for you is the second part, which is the ranking component, because it cares about the inter-document similarity. Of course, we use hinge loss for that. And the goal is that we want similar documents. The goal is to have short Hamming distance. And you know Hamming distance, it's just a number of differing bits. And we minimize weighted average Hamming distance like this: 1/4 of wij yi minus yj squared. So you can say it's 1/4 of trace of y transpose ly. And if you look at my playlist about spectral graph theory, I talked about Laplacian, which is d minus w, and all of those classical things. But one interesting thing is that we have another stuff. We have spectral hashing, which I see it as an extension of spectral clustering. How? You just need to subject it to y of ij. A constraint should be like this: it belongs to -1 and 1. And that's why it's now spectral hashing. So the same methodology, but now we have one more constraint, which is very strong constraint, because it says yij is either -1 or 1. So most methods focus solely on generating document representation and do not rank documents based on their hash codes. So the goal of variational components is to maximize likelihood of its generated hash code and sample the hash code from Bernoulli distribution. But the goal of the ranking component is learning to rank documents correctly. But both of these components are optimized jointly in a combined neural networks. And the goal of the final model is to generate hash codes solely based on new unseen documents. So what is ranking-based semantic hashing? As I said, locally sensitive hashing is not good because it is data independent, and so your hash codes could be to the m, because m is the number of bits of the code, and you have a encoder. You have some documents. You have then in the decoder you have some reconstructed documents. And your z is here. Your z, what you want to do is q of di minus mu I. And mu I is drawn from uniform distribution. So during training, that ranking-based semantic hashing, RBSH, takes document triplets, D, D1, and D2, as inputs with estimated pairwise. So your input is not only this triplet, but also pairwise similarities. What is important is if we do it for each input D. So you have two kinds of input to the model. And this is a concept that is often called weak supervision. And the product, and you can also predict either D1 or D2 is, for example, it is most similar to D, for example. And so the encoder, so in the encoder you have Q of D, and then like the variational inference Z and F of Z, but it's drawn from Bernoulli distribution of Q of D. And Q of D is the sigma, which enforces the output to be between 0 and 1, and Wm V2 plus Bm. So what we want to minimize is the ranking error. So the loss that we care is just the maximum of 0 and epsilon minus sine of D and D1 and D2, D of D1, D and D1 and D2, if their S, D and D1 is different from S, D and D2. And otherwise it's just D of D, D1 and D2. And this sign is just Z minus Z2 minus Z minus Z1. For example, for any document that you say, document D, as I said, we compare it to all of the documents and rank them based on that. For example, we have imagine that we have only 4 documents, D4 and D3. So your ranking could be D3, D1, D2, and D4. And if we want to preserve these semantic meaning by preserving their distances, so if you combine variational and ranking component, we have a loss. This is for rank, as I said, and you have another loss, which is EQ of the same thing that you have done for variational inference, variational autoencoder, Q of. So your loss is dependent. This is the scale you scale it because you want to have a trade-off between your rank loss and the other component loss, so you scale it. And then you have the rank loss, but then you have 2 other terms which is related to variational component, which is EQ of sigma log of P of omega j given F of Z plus beta. This is another scaling parameter for KL loss. As I said, you really care about trade-off between the different terms, the rank component and the variational component. And so beta, KL divergence of Q of Z given D, P of Z. And then we have another article in 2021 from the same authors in Copenhagen University, but it is approaching it from a very different perspective, and the title is Unsupervised Multi-Index Semantic Hashing. But in multi-indexing, it is an approach that constructs a smaller candidate set to search over, which of course can lead to sublinear search time. So semantic hashing traditionally uses spectral clustering, latent semantic indexing, and those things, but the modern version uses deep learning and unsupervised autoencoder architectures that I talked. So the modern version, the efficiency is small. It uses brute force linear scan over all hash codes because you don't want to go to do a linear scan over all hash codes, but you want to use a wiser version. You can enable sublinear search time by just constructing a smaller set of candidate hash codes to search over. And that is the solution of multi-index hashing. You make it sublinear. The complexity is reduced significantly. And what is self-taught hashing? It's just learning to preserve the local structure between samples identified by an initial k-nearest neighbor search in the original document space. Of course, this article is inspired by another article, which is written in 2014 by Mohammad Nourouzi in Toronto University. And it's about, the title is Fast Exact Search in Hamming Space with Multi-Index Hashing. So the code, we know that the code's longer than 32 bits. If it is more than 32 bits, are not being used. And it was thought to be ineffective. So we built multiple hash tuples on binary code substring that enables exact k-nearest neighbor search in the Hamming space. So we get sublinear runtime. So now we have an example is like this. This part is, we call it substring, and it's a hash tuple. Itself, it's a hash tuple. Another substring 2, is a hash tuple and some buckets, and another substring 3 is hash tuple. Substring 4 is hash tuple. Of course, many of these things are empty. Many of them are very dense. There are lots of items inside each of them. And you know these things from computer science. But now what we care is we have multiple hash tuples. So on databases up to 1B codes, multi-index hashing is hundreds of times faster than linear scan. So it can be dramatically faster than exhaustive linear scan. And a binary code is and of course you can read the algorithm. There are 2 algorithms on that paper. But let's get back to the previous article that I talked about in Copenhagen University. It was about multi-index semantic hashing. So it learns to generate an n-bit hash code. So ZD is in -1 and 1. It's n-bit, and it represents the semantics of that. So we reduce the number of documents per hash table lookup. We derive an objective that maximizes the Hamming distance between the particular substrings of ZQ and ZS. ZQ is the query, ZS is the sample. So we reduce the number of such false positive matches in the hash table lookups. So Z